Hello everyone. In this video we are going to discuss about the design criteria of your grid chamber. Grid chamber, which is one of the unit operations carried out during the treatment of sewage. Okay, so this is the topic of environmental engineering. So I'll discuss about the design criteria here in detail, and then we'll discuss a numerical problem which is based on the design of grid chamber in this video. Okay, so let us first of all discuss some points, some important points in grid chamber. So it is the second unit operation used in your primary treatment of wastewater after screening. Okay, so we have different treatments in sewage treatment plant. Those are your primary treatment, secondary treatment, and then your final treatment. Okay, so in the primary treatment we have certain operations. So first operation is your screening operation, in which we use bar screens to separate out the bigger particles, bigger materials that is present in your sewage. Okay, so we all know that sewage, first of all we collect all the sewage from your houses and your industries, and then we take all those all that sewage or wastewater to the treatment plant for the treatment of the sewage, so that we can withdraw the effluent into the river. Okay, so your treatment is very much important before directly you're disposing of the effluent into the river. Okay, so here this grid chamber is your second unit operation after your screening operation. Okay, so it is intended to remove your suspended inorganic particles such as sandy gritty matters which is present in your wastewater. Okay, and we know that we have a sewage consists of two important matters. One is your organic matter, which is decomposable and which get decomposed after certain period of time interval, and another one which is non-decomposable, that is your inorganic particles that need to be removed from the sewage. Okay, so the inorganic particles we remove in this operation. Okay, in the grid chamber. Now this is usually limited to your municipal wastewater, generally not required for your industrial effluent treatment plant. Okay, so we use this grid chamber mostly in your municipal wastewater treatment. Okay, we don't require this unit in industrial effluent treatment plants, except in some industries where there might have a grid in the sewage. Okay, so we all know that the gritty particles come into the wastewater due to storm drainage. Okay, so when storm drainage get mixed with your sewage, then this the quantity of your grit material, it increases in the sewage. So this is very much important to remove this these gritty materials from the sewage, because in the further unit operations, when we are going to use some mechanical devices, so these grit, if it is present in the sewage, your effluent, then it is going to make a wear and tear of the mechanical devices. Okay, so we need to remove it. So the grit consists of your sand, gravel, and some other heavy solids which are present in the sewage, and which have a higher specific gravity. Okay, so those of your organic solids are very present in the sewage. Organic solids come from your kitchens, bathrooms, or from the washrooms of your houses, and inorganic material that generally comes out from your storm drainage into the sewage. Okay, so the specific gravity of these organic matters is very much less than that of inorganic matters. So grit consist of your sand, gravel, and other heavy solids which have higher specific gravity. Okay, so these are some points in the grit chamber. So now another point we'll discuss here is your horizontal velocity in the inflow, horizontal velocity inflow through the grit chamber. Okay, now in the grit chamber, generally we use sedimentation process. Okay, the particles, the heavier particles, get settled down at the bottom. Okay, so the settling of these grit particles in the chamber, it is assumed as your particle settling. Okay, it is assumed as particle settling as individual entities. Okay, we consider that every particle is settling in the grit chamber, and it is referred to as type 1 settling. Okay, so in the grit chamber, the settling that occurs is called your type 1 settling. Okay, so the grit chamber, it is divided into 4 compartments. Okay, first one is your inlet zone, second is your outlet zone, and third one is your settling zone, and then the sludge zone. Okay, so I have drawn a diagram here to make you understand all these zones which are present in the grit chamber. So this is your zone 1. Okay, this is your inlet zone. So in this zone, this zone, it distributes the incoming wastewater uniformly to the entire cross section of the grit chamber. Okay, when your wastewater enters into the grit chamber, so it firstly enter into your zone 1 of grit chamber, where this whole wastewater is get uniformly distributed to the entire cross section of the grit chamber. So this is your first one, that is zone 1, inlet zone. Okay, now second zone is your outlet zone. Okay, so this is the second zone. So in this zone, this zone collects the water after grit removal. Okay, so in the first zone we collect the water, and in the second zone the water is collected after the grit removal. Okay, so now third zone is your called settling zone. Okay, this is the third zone, this middle one. Okay, this is your third zone. So in the settling zone, the settling of grit material takes place. Okay, so first of all, your wastewater will enter through zone 1, and then it will enter into zone 3. Okay, so in zone 3, the settling operation of the grit material will occur. Okay, so after that, final zone is your zone number 4, this zone. So this is your this is your sludge zone. Okay, in which all this grit material get settled down, and the settling of your grit takes place in this zone. Okay, so these are the 4 compartments which are present in your grit chamber. Okay, please note it down. Now L is the length of the settling zone. Okay, this is the length of the settling zone, and H is the depth of the settling zone. Here, this H is the depth of the settling zone. Okay, and V is the horizontal velocity of the wastewater. Okay, so here the wastewater will enter into the grit chamber with velocity V. Okay, and V naught is the settling velocity of smallest particle intended to be removed in the grit chamber. Okay, so let V naught is the velocity of the smallest particle that we want to remove from the wastewater. Okay, so the smallest possible particle which is present in the your sewage, we want to remove it, so hence its a settling velocity, we are taking it as V naught. Okay, so now if your Vs is your settling velocity of any particle, okay, so V naught is the settling velocity of your smallest particle intended to be removed. Okay, so if suppose this is your tank, this is your grid chamber, zone number 3, where the your wastewater has been collected for grid removal. Okay, zone number 3. So in this wastewater we will have inorganic particles, various amount of inorganic entities which will be present. Okay, so these entities will have certain settling velocities. Okay, and the settling velocity depends upon the size of the these entities. Okay, so let us take the settling velocity. V naught is the settling velocity of the smallest particle which will be present. Okay, so the smallest particle now which will be present in the this wastewater. Okay, and Vs is the settling velocity of any particle. Okay, so we want to derive the equation for the settling velocity. So let us take Vs is the settling velocity of any particle which is present. So for Vs greater than equals to V naught, okay, these particles will be totally removed. Okay, this if the settling velocity of the particle, it is greater than or equal to the settling velocity of the smallest particle which is present in the sewage, then your all of the particles which are present in the sewage will be totally removed. Okay, this is the first condition. And if your settling velocity of the particle, it is less than your V naught, that is the settling velocity of your smallest particle, then these particles will be partially removed. Okay, so these are the two conditions. Okay, we are deriving the settling velocity here for the grid chamber. So we are taking Vs as the settling velocity and we are comparing it to the settling velocity of the smallest particle which we want to remove from the grid chamber. Okay, so now the size of the smallest particle expected to be removed in the grid chamber, it is 0.2 mm, or sometimes it is less than 0.2 mm, or it is up to 0.15 mm. Okay, so these are the standard limits of the smallest particle size whose settling velocity we are taking as V naught. Okay, so this is the smallest size particle. If we want to remove this particle, then the velocity settling velocity for this particle, we are taking it as V naught. Okay, and Vs is the your settling velocity for the grid chamber. Okay, so settling velocity, if the settling velocity in the grid chamber, it is greater than or equal to the settling velocity of this particle, the smallest particle which is present in the sewage, then all of the matter will be removed from the grid chamber. Okay, and if it is less, then the matter will be partially removed. Okay, so we discussed this. So now let V naught is the terminal velocity with which the smallest particle will settle. We have discussed this is called the terminal velocity. Okay, terminal velocity is the settlement of your particle. Okay, the velocity with which the particle get settled down. Okay, so this velocity can be expressed as your flow or discharge per unit area of the tank. Okay, so this terminal velocity, that is V naught, it is expressed as your flow or discharge per unit area of the tank. Okay, surface area of the tank. So also it is called as a surface overflow rate, SOR, or surface settling velocity. Okay, so we term these to this terminal velocity as your surface overflow rate or surface settling velocity. Okay, now for 100% removal of the grit from the wastewater, Vs should be greater than equal to V naught. Okay, so here comes another term, that is the detention time. Okay, so detention time is the time for which the time period for which we let the sewage water undisturbed in the grid chamber, so that the particles get settled down at the bottom. Okay, so this is your detention time. So the detention time, it is given by L over V. That is L. What is the L? L is the length of your settling zone, and V is the velocity of your wastewater, and capital H is the depth of the settling zone, and V naught is the velocity of the smallest particle. We have discussed all these parameters. Now we'll rearrange this. Then L over H is equal to V over V naught. Okay, so now to prevent your scouring of already deposited particle, the magnitude of V should not exceed critical horizontal velocity. Okay, here comes a new term, that is critical horizontal velocity, which is represented by Vc. Okay, what we are saying here is that when this settling of your grit particles takes place in the grit chamber, these particles get settled down at the bottom. Okay, so to prevent the scouring of these already deposited particles, okay, the magnitude of V, what is V? The velocity of wastewater. Okay, the magnitude of V, it should not exceed the critical horizontal velocity. Okay, so it should be within certain limits, so that your scouring of this material will be prevented, because if the scouring action takes place, then the efficiency of grid chamber will be definitely affected from this. Okay, so above equation becomes, this equation becomes L over H equal to Vc over V naught. So we are replacing here this velocity, that is velocity of wastewater, by critical velocity. Okay, so this critical velocity is very much important. Now the critical velocity, it is given by the following equation. Vc is equal to under root of 8 beta over f g s minus 1 into d. Okay, what is beta? Beta is a constant. Okay, so this beta, it depends upon the type of the material which is present, characteristics of the material, your inorganic matter which is present in the sewage. So for granular sand, we use this value as 0.04, and for sticky material we use 0.06. okay, the value of this beta. Now F is your Darcy V-spec friction factor. Okay, we use Darcy's V-spec equation in fluid mechanics. Okay, so here this F is the coefficient. Okay, this is your Darcy V-spec friction factor. So its value is 0.03 for your gritty matters. Okay, we take the value as 0.03, and for what is G? G is your gravitational acceleration. You all know that. S is the specific gravity of the particles to be removed. Okay, so the specific gravity of the particle which is present in the wastewater, which we want to remove in grit chamber, so that is the specific gravity, and it is generally 2.65 for sand. Generally the gritty material is always sand, so we are taking it as 2.65. and what is capital D? Capital D is the diameter of the particle. It is in meters. Okay, so now the grit chambers are designed to remove the smallest particle. We discussed it. So the size of the particle is 0.2 mm with your specific gravity around 2.65. okay, so this is the and generally the material which is present is sand, so the specific gravity is 2.65 for sand. And so by using the above equation, by using this equation, we can calculate value of Vc, critical velocity, for the size 0.2 mm and with specific gravity 2.65. we can take the value 0.228 meter per second. So hence the critical velocity of the particle coming out here is 0.228 meter per second. Okay, so the velocity of flow should be less than this velocity, so that your scouring of the already deposited material in the grit chamber can be prevented. Okay, so this is very much important in grit chamber design. Okay, So next thing we are going to discuss here is your settling velocity of the particles. Okay, so what is the settling velocity of the particles? The particles which are present in your wastewater, they have different settling velocities. Okay, so these velocities depends upon the individual characteristics of these particles and also on the characteristics of the fluid. Okay, so as the sewage consists of mostly your 99% of water. Okay, so your characteristic of fluid also plays very much important role in settling velocity. Okay, so the settling velocity, it depends on your individual characteristics of the particles and also on the characteristics of the fluid. So it is given by your Vs, that is settling velocity, as 4 by 3 small g over CD capital S minus 1 into D. Okay, what is your Vs? Vs is the velocity of settlement, and what is CD? CD is your Newton's drag coefficient. Okay, and it is given by 24 over r plus 3 over under root of r plus 0.34. Okay, when the value of your r is greater than 0.3 and less than 10 raised to power 4. Okay, so this is the value of CD we are going to use when your Reynolds number is between 3 to 10 raised to power 4. Okay, and if it is less than 0.3, then the value of your Reynolds number, it is less than 0.3, then we are going to use 24 by r, the value of CD, that is Newton's drag coefficient here in this equation. Okay, so r is your Reynolds number and it is given by rho vd over mu, we know that, or v over vd over nu. Okay, this is your nu. What is mu? Mu is your dynamic viscosity. Okay, and it is given in Newton second per meter square, and nu, it is your kinematic viscosity, it is meter square per second, and it is represented, if we want to convert this mu into nu, then nu is equal to mu over rho. This we use this relation. Okay, so these all are the properties of your fluid. Okay, so in this number, this is very much important number. Okay, so Reynolds number, so by calculating this Reynolds number, we can define the fluid. Okay, in your fluid mechanics. So here we are going to use this Reynolds number concept here. So in this velocity, we did it, that is in this equation, that is settling velocity equation, we are going to use this drag coefficient, which is dependent upon this Reynolds number. Okay, now for your Reynolds number less than 0.3 and CD, for Reynolds number less than 0.3, your CD is 24 by R. Okay, so if we put this in the above equation, in this equation, then what the equation, the resulting equation that we get is called your Stokes law. Okay, so this is the Stokes law. So what it says, whenever a particle, okay, generally we take the particle to be spherical. Okay, spherical in nature. So if a spherical particle moves downward in any fluid, then it moves downward with a certain velocity, which is called your settling velocity, and it is given by this equation. This is your Stokes law. Okay, because it will when this particle will move down, okay, then it will experience some drag which is offered by the fluid. Okay, and it depends upon the fluid characteristics also. So that's why we discussed here in the in this concept that the velocity, it depends upon individual characteristic of the particle and also the characteristics of fluid, because the fluid, the viscosity of the fluid, it also influence the settling velocity of the particle. Okay, so when your R is greater than 0.3, Vs should be worked out by trial and error. Okay, so if your R is your less than 0.3, then we are going to use this equation, and if R is greater than 0.3, then we are going to use the value of CD as this, and we are going to calculate the value of VS by trial and error method. Okay, so with the variation in sewage flow, okay, so with the variation of variation in your sewage flow received at the treatment plant, it is important that the velocity of wastewater in the grate chamber, it should be maintained nearly constant. Okay, otherwise if velocity is lower, then the deposition of organic matter along with the inorganic solids will occur. And if the velocity is higher than the critical velocity, as we discussed, okay, so if the velocity is higher than your critical velocity, then the scouring of already deposited grit material will occur, leading to the failure of performance. Okay, so hence for proper functioning of the grit chamber, the velocity should not be allowed to change, okay, in spite of change in flow in the grit chamber. Okay, so this can be achieved by the provision of your proportional weir or partial flume at the outlet end of the grit chamber. Okay, so that you can check in your books. So in the designing of your grit chamber, your critical velocity as well as your settling velocity of the particle, it is very much important, because basically grit removal is a sedimentation process in which the gritty particles get settled down at the bottom of the tank, and the settled material, it is called your sludge. Okay, sludge which is collected in the at the bottom of the tank. Okay, so these are the design criteria. So now here I am going to discuss one important topic also, that is your disposal of grit. Okay, so after collecting the grit at the bottom of the grit chamber, we need to dispose of. Okay, so about 0.004 into 0.004 to 0.2 meter cube per million liter of your grit is collected at the sewage treatment plant. So quantity of the grit is more, particularly for your combined system. Okay, so combined system, if we are using combined system, then the quantity of grit will be more. Okay, so the grit collected can be disposed of in the following manner. Okay, we can dispose it in the following manner. So we can just in large treatment plant, grit is incinerated with your sludge. So whatever is the sludge we are collecting from the treatment plant, we use to incinerate the grit particles along with the sludge itself. Okay, so in the past we used to screen out the grit, and then we used to dump it into the sea. Okay, so this was the our past practice to dispose the grit. Okay, so generally we don't practice this nowadays. So also generally grit should be washed before the disposal to remove the organic matter. Okay, so organic matter, sometimes the organic matter also get collected with the grit, so we need to remove those organic matter before disposing of, because organic matter are the only material which are present in the sewage that create the nuisance. Okay, in the sewage. So this because they undergo decomposition. Okay, so this grit should be washed before the disposal, and after that we can land dispose. We can opt the land disposal of your washed grit. Okay, so this is the most common practice we use nowadays. Okay, so this was the design. This was the design aspect of your grit chamber. So let us take an example of the grit chamber design. So here is the problem. Given problem is a channel type grit chamber has a flow through velocity of 0.25 meter per second, a depth of 0.8 meter and a length of 10 meter. For inorganic grit particles with specific gravity 2.5, Determine the particle size that can be removed with 100% efficiency. Assume nu, that is kinematic coefficient of kinematic viscosity, as 1.01 into 10 raised to power minus 2 centimeter square per second. Okay, so this is the given problem. So let us solve this problem. So here, first of all, what is given to us? We are provided with the velocity of flow, that is 0.25 meter per second, and the depth of the flow is also given, that is 0.8 meters. Okay, and the length of your settling zone, it is also given as length of the tank is also given as 10 meter. Okay, now the specific gravity of the inorganic grade particle that we need to remove, it is given as 2.5. This is also given, and the particle size we need to calculate. Okay, so this is in the question, we need to calculate the particle size. Okay, so we are also provided with the kinematic viscosity, 1.01 into 10 raised to power minus 2 centimeter square per second. We'll change it into meter square per second, 1.01 into 10 raised to power 6 meter square per second. So let us take the diameter of the particle as d. As we have discussed, we always take the particle to be spherical. So let us take the diameter of the particle to be capital D. Okay, so let Vs is the settling velocity of the particle. We have discussed, okay, this in the designing procedure, and let for 100% efficiency, okay, so Vs should be greater than equal to V naught. We have discussed it also. Okay, so to remove all the organic matter, that is to achieve 100% efficiency, the velocity of your settling velocity of the particle, it should be greater than equal to V naught. What is V naught? V naught is the settling velocity of the smallest particle which is intended to be removed. Okay, that we have already discussed it while discussing the design criteria. Okay, so also detention time is L over H equal to V over V naught. Okay, we know that, or L equal to L over H equal to V over Vs. Okay, now we'll replace here V naught with Vs. Okay, so the this is the Vs is the settling velocity of the particle. Okay, so now we are provided with the L we know, that is 10. We'll put all the values here. H is 0.8, V is 0.25, it is also given, and Vs we don't know. Okay, so we'll calculate from here. First of all, Vs. Okay, so Vs will come out to be 0.02 meter per second. Okay, so I hope this step is very much clear. Now the settling velocity of the particle, it is given by Vs equal to 4 by 3 G over CD S minus 1 into D. We have discussed it. So the value of R, that is less than 0.3, CD is 24 by R. So above equation becomes the Stokes law. Okay, R is the Reynolds number and CD is the drag coefficient. Okay, so let us take the here, for instance, R is your less than 0.3. Okay, so for this case we are going to use the equation as Vs equals to G over 18 S minus 1 over V multiplied by D square. Okay, what we are assuming? We are assuming the Reynolds number to be less than 0.3 here. Okay, so this becomes the Stokes law. Okay, now we'll put the value of Vs here, that is 0.02. We'll put all the values, G 9.81 upon 18, 2.5 minus 1 into 10 raised to power 1, 1 into 1.01 into 10 raised to power minus 6 D square. Okay, we'll calculate by solving this. We can calculate the value of D from here. So D will come out to be 1.24 into 10 raised to power minus 7 meters. Okay, so or your D is coming out to be 1.24 into 10 raised to power minus 7 into 10 raised to power 6. We'll convert it into micrometer. Okay, so the particle size is coming out to be 0.124 micron. Okay, so as the particle size of 0.124 micrometer or microns can be removed with 100% efficiency in this grid chamber. Okay, so I hope now the problem is clear and you have understood all the design steps which are involved in grid chamber design. So do practice more and more problems on the design of a grid chamber, and if you face any type of problem you can write to me on my email, and also you can write the problem in the comment section. Okay, and do take care of yourself everyone. Thank you so much.